Let's talk about another sorting algorithm. Let's review what we have covered so far in the course. We have covered the quadratic selection sort and insertion sort. We covered the n log n merge sort, and also we covered the recursive quick sort, which in the best case will be n log n. However, in the worst case, where the pivot was not chosen wisely, is going to be quadratic, just the same as selection sort and insertion sort. That's what we have got so far. We have learned about 4 sorting algorithms. The heap sort algorithm is going to solve the same sorting problem, and we're going to see about its running time in just a moment. And this will be just our 5th and last algorithm for the course. And I think beyond this course, I don't think you will learn that many more sorting algorithms. So definitely in this course, you have learned about all you are supposed to know as a CS or software engineering graduate. Congratulations. So I think it's really exciting to learn about everything you're supposed to know about sorting. And for the heap sort algorithm, it's actually would be considered as a more advanced sorting algorithm, because in order to really do it, you need to understand, of course, about how the heap works. That's why we actually have spent so much time earlier to really systematically and thoroughly go over what a heap is like, its properties, and also how we can perform the various operations on the heap, and also how to construct the heap, either top down or bottom up. And we have now paved a very solid ground for talking about the heap sort algorithm. The algorithm itself is actually incredibly straightforward, given that you actually understand what a heap is. Let's now talk about the heap sort. And the sorting problem is, as expected, as we have seen many times, and the same sorting problem. And let's say we want to sort in a non-descending order. So it would be very nice if we can keep somehow extracting the minimum elements from the input so that we can somehow put things into the sorted order. That's kind of what we learned from the selection sort idea. You can think about, in some way, heap sort does share some similarity with the selection sort, because we want to keep selecting something from the heap, the tree, right? That's something you can keep in mind. I'll write it down as well as a remark. It's always important to connect the dots and see how one algorithm might share some similarity with another. Alright, so the heap sort algorithm consists of 2 phases. Phase number 1, we're going to construct a heap out of n entries in the input array. The n will be the size of the heap ultimately, how many nodes you're going to store in the tree. How do we do that? Well, actually we just learned about how we can construct a heap out of n entries that's given. Either the entries may be supplied one at a time, in which case we'll do top-down heap construction. If the entries are supplied all at one go as an input array or input list, in that case, the construction will be bottom up, which will take bigger of n, right? So these are the 2 approaches you can choose, right? Approach number 1 and approach number 2, right? So these 2 are what we just covered before we talk about the heap sort algorithm currently. Right? Approach number 1, top down, and also approach number 2, bottom up, right? And one will be n log n, and the other one will be n. Intuitively, it should be a no-brainer to actually choose approach number 2, in which case you can definitely get a strictly more efficient construction mechanism. I agree. However, as we said before, the reason that we have to talk about approach number 1 versus approach number 2 is because there is certain implicit assumption you have to make about how the input is supplied. If the input is only supplied one entry at a time, in that case, you may have no choice but go for approach number 1, because you want to build a heap along the way. That input entry is supplied one at a time. So you have to judge. But it turns out, asymptotically speaking, the running time is going to be dominated by phase number 2 anyway. So even if you actually make the phase 1 more efficient by choosing the linear time, it's going to be dominated. It's going to be dropped when you actually derive the running time anyway. Right? That's something I want to mention. Right? You always want to know what's going on, and whether choosing the more efficient algorithm is really worth it, or it's not going to make a difference ultimately anyway. But it's always good to know what's available to you. That's about phase number 1. Let me draw that very quickly. Right? And by the way, for heap sort algorithm, unlike the previous sorting algorithm, you wouldn't be provided any source code. So I think for the best of your learning, you really have to go back to the earlier part of the lecture and see how you can implement a heap. I will give you some tips about how to implement the heap using an array. But based on what we have learned earlier, we know how to represent a tree using the link node data structure. So you should really use both. You want to use the link node data structure to implement a heap and try to implement the insertion, deletion, bottom-up, top-down heap construction mechanism, and etc. You want to do those on your own. That's really the practice you have to go through. If I just gave you the source code, I don't think you are going to click as much as if you just do the exercise on your own. And then in the next part, as a look ahead, we're going to see an alternative way for implementing the tree structure using an array. That'll be also interesting to see. Right, so that's why for this part, I'm only going to walk over with you about the high-level idea about a heap sort, which will completely make sense. But to really fill the gap about making some working system, you have to implement the Java on your own. Let's talk about phase number one. Let's say we are given this input array or input list is simply a list of n entries. Meaning that the size is simply just capital N, let's say. That's the input. And phase number one, we're going to construct a heap out of the input. Construct a heap out of n entries. And over here, it can be either approach number A, or let's say A or B, right? Or 1 or 2. Either you can go for A or you can go for B. Right? So for A, it's going to be top down. And for B, it's going to be bottom up. And we spoke about each of them in detail already. And for the top down, you're basically going to start with the root and then keep growing the heap in kind of this way, and etc. That's what you will do. And for the bottom up, you're actually going to start with the level H root, so level H nodes, and then you try to build gradually, like this way, right? You really want to see exactly what I'm doing here, and then eventually get to the root. That's the bottom up. And let's review quickly about the running time. For the top down, this approach over here is basically just about exploiting the insertion and deletion, which will take actually insertion only. It's basically exploiting the insertion method for the heap data structure, which will take log n each time. And because you're going to keep inserting until you actually got all the n entries covered, in that case, it'll be n times log n. So this one here is going to be big O of n log n. What about approach B? A very quick recap. That one there is actually going to, since we're going to go for bottom up, and the intuition that we actually remarked earlier is, since you try to start with the bottom one should really got the most number of nodes. So for the level H, you would have already covered close to 50% of the nodes already. And the second last level, you will cover another 25% and etc. So that means most of the nodes are really constructed or integrated into the ultimate heap with a relatively cheap cost because the height of the tree is not that high yet. In that case, it's going to be big O of n. So let me use the green to indicate that if you really have a good, if you really can have an option to really choose between A and B, you definitely should choose B. Even though, as I said, phase number 2 is going to dominate the running time anyway. Hey, let me be more consistent with the spelling, since we talk about capital N. So this one should be capital N log n. All right, so that's about step number 1, phase number 1. What about phase number 2? The phase number 2 would be, once you have built out the heap, you have to somehow exploit the relational property of the heap. Before I show you the slides, let's talk about what we should do for phase number 2. Exploit the heap order property or the relational property. Either way, they may be used interchangeably. What is the relational property for the heap, right? Remember, there was a single slide that we actually discussed to go over the different properties. One of them, which is very, very fundamental for a heap, is the root of the heap always store the entry with the smallest or minimum key value, denoting the maximum priority, right? The root stores the entry with the minimum key value. That's really the most fundamental relational property you have to keep in mind. The heap order property, which talks about the root with the minimum key. What does that really mean? I want you to recall what we did in the selection sort. Right? So this part over here is a little bit analogous to the selection sort, even though the running time ultimately is going to be more efficient than selection sort. But I want you to just think about the mechanism that we used, selection sort. And if you can recall, let me just put a side notes over here. When we talk about selection sort, if you can just go back to how I did the visual illustration for the selection sort, we said that initially the array is unsorted completely, and we try to ultimately maintain some portion of the sorted area, let's say. And also this part over here in the pink will be the unsorted area. What we gotta do is every time, if you want to grow the sorted area by 1 element, you have to choose among the unsorted area the minimum elements and put it to the end or to the beginning of the sorted portion, right? That's really the fundamental step for the selection sort. Okay, I want you to just recall that insight, because we're using that same mechanism for the heap sort as well. So we simply say select the minimum from unsorted portion and put it to the front or end of the list. Well, here I'm giving you some flexibility over here. If you always put the minimum to the front of the list, in that case, your ultimate list is going to be in maybe a descending order. If you keep inserting the minimum element into the end, you're going to result in a non-descending order, right? That's kind of what we said earlier. I'll let you recall the details, maybe review the detail about selection sort. And for heap sort, we're going to do something identical for the second phase. Okay, for second phase, let's see. Let me just go back to the slides, and then we'll talk about the second phase. We want to delete the n entries from the heap, because we know that each deletion is actually going to extract the root, which stores the entry with the minimum key value. So that means we will be able to keep getting the minimum value from the entire entries collections. In that case, we keep getting the minimum, just like selection sort. We can definitely get a sorted sequence of the entries. That will be the idea for the second phase, right? And each deletion is going to take a big of log-in time. If you recall, for insertion and deletion, both of them will take log-in time. Why does the deletion take log-in time? It's because once we have replaced the root, let me just talk about it quickly. Right, so the idea would be you get some heap over here. Let's say this is the heap. And you keep extracting the root, meaning that the tree is going to become smaller and smaller and smaller. Ultimately, you're going to delete the last node from the root, and then the resulting entries that return from the deletion is going to form a sorted sequence. Right, so that's why I'm going to write it down. Right, so you're going to keep deleting the root until the heap is empty. And the first deletion is going to give you the absolute minimum. The second deletion is going to give you the second minimum, and etc. And the last node that's left in the heap to be deleted will be the maximum of the original heap, right? And why would that take log-in time? The reason is for the very first one is going to be the most expensive, because the height for the tree will be just the maximum. of the original tree. Of course, once you get to a very small heap, let's say only a one node heap to delete, in that case, it will only take constant amount of time, right? So to really work out the running time, I'll leave that to you about this portion over here to really delete so many times. But every step is going to be dominated by just log n, just upper bounded by log n. For the very first one, after you have replaced the rightmost node at the level h and replace it for the root, and then you're going to do a down heap bobbling, in the worst case all the way to the bottom of the tree. So that's why it's log n, right? It's going to be big O of log n. And how many deletions do we have to do? Well, since we got n entries in the tree, in that case we're going to do n deletions. And each one of them is going to take log n. So ultimately, we're going to get big O of n log n. That's what you will have. Right? Let me just fix this one here quickly. Okay, n log n. That will be the running time for the second phase. And so let's now compare the different running time over here. For the first phase, you actually got either n log n or n. And for the second phase, you got exactly n log n. What will be the overall running time? Apparently, you can see that the second phase is always going to dominate running time. So even if you chose the bottom-up heap construction in the first phase, which will be n, is going to be dominated by n log n anyway. But of course, if you can make one phase more efficient, why not? Even though the ultimate theoretical upper bound wouldn't change, right? That's something you want to remember as well, right? So ultimately, the heap sort is going to be n log n, big O of n log n. Of course, you have to also make sure you understand very well about the derivation process for the running time. All right, and let's now move back to the slides. Right, so first deletion, extract the minima, etc., and the running time will be n log n. Right, and that's about the discussion I would like to have about the heap sort. You can see the algorithm itself is actually very straightforward from the top level. You simply create a heap and keep deleting the root. However, in order to really understand why the algorithm is actually correct and efficient, you have to understand all the background details about what a heap is, what a binary tree is, and also what the various properties are, in order to appreciate about the efficiency and simplicity of this algorithm. Alrighty, and that's about it. And let's now move on to how we can implement a heap or binary tree using an array.